Hello, my name is Kathy Joseph, and I'm a science historian and novelist, and it is my honor to welcome you to the Norman Lockyer Observatory. The people at the observatory thought you might get more from this experience if you knew a little bit more about Norman Lockyer and how he did his amazing experiments. So I put together this little video. I hope you enjoy it. I'd like to begin in around 1861, when Norman Lockyer was a bored 25-year-old second-class clerk and linguist for the War Office in Wimbledon, England. That was when Lockyer became friends with a man who had bought a small telescope that he wasn't using. And the friend loaned the telescope to Lockyer, and Lockyer was instantly hooked. Soon the young man bought his own cheap telescope. His observations were enough to get him admitted to the Royal Astronomical Society in 1862, but it sure didn't pay the bills. However, that same year, he met a telescope manufacturer named Thomas Cook, who was so impressed with Lockyer that he promised him a 6¼ inch lens if Lockyer could build his own tube to hold it, which Lockyer did with paper mache, held up the whole thing with scrap metal. An improved version of this telescope, which he made in 1871, is still in use today. The second thing that happened is in that same year of 1862, a neighbor asked him if he would be the science editor for a new magazine called The Reader. He was hired because he was smart, hardworking, knew a lot of people by this time, at least in astronomy, and as one of the owners said, he will do the work too gladly at a lower figure than any other competent man. Soon Lockyer contacted every famous scientist in England to try to get articles for his paper, including Charles Darwin and his very influential friends. Lockyer's wife, Winifred, also got into the writing business when she helped her husband translate a French book of astronomy called The Heavens, which her husband edited in 1867. Winifred Lockyer was so proficient at translation, and her husband was so busy, that she started to do more translations, and she was finally credited for her work. Winifred's translations and Lockyer's writings kept them in the black, but barely. Meanwhile, at about the same time period, they learned about a new method to study the stars called spectroscopy. Spectroscopy is when you separate the light from a burning object into its different colors with a prism or diffraction grating to determine its chemical composition, which is how we know the composition of the stars and sun. Let me explain. See, in 1859, a German scientist named Robert Bunsen used his new Bunsen burner to study the colors the chemicals made when they were burned, and found that burning solids and liquids basically make a continuous rainbow, but burning gases make distinct bands of light, an optical fingerprint, so to speak, where each element produced its own distinct bands. Bunsen also found that sodium gas would produce distinctive double bright yellow lines, and as it only produced those two colors in the visible spectrum, these bands were particularly bright. In fact, it was so sensitive it could detect sodium when as little as 1/20 of it was suspended in smoke. Then Bunsen's friend Gustav Kirchhoff had the random idea of burning sodium in front of a lamplight. As his lamp produced basically a continuous spectrum, and the sodium gas produces those two bright yellow bands, Kirchhoff assumed that this combination would produce a rainbow with extra bright bands superimposed on it. Instead, he was shocked to look at the yellow part of the spectrum and find two dark black bands, quote, exactly at the spots where the bright lines were supposed to show. Kirchhoff immediately realized that he had the solution to a 45-year-old mystery of lines in the sunlight called Fraunhofer lines. See, back in 1814, a lens maker named Joseph Fraunhofer found that when you look really, really closely at sunlight after it's gone through a prism, you see a rainbow with dark shadows in it, with two lines in the yellow at the exact same spot as the bright yellow from burning sodium, labeled the D lines, as they are the fourth major dark lines in sunlight. Therefore, in 1859, Kirchhoff realized that the center of the sun must be producing a continuous spectrum, like his lamp, and the gases in the sun's atmosphere must be absorbing the particular frequencies depending on its element. Therefore, all you needed to do was find the bright lines that elements make on Earth, find the corresponding dark lines in the sunlight, and presto changeo, you know what's in the atmosphere of the sun. This was the first method found to know the composition of the sun or the stars, and it is still a staple of astronomy today. Bunsen and Kirchhoff found not only sodium, but also hydrogen, iron, and even gold lines in the sun, but no helium, as no one knew about helium yet. Back to Lockyer. Through his publishing work, Lockyer met and became close friends with a Scottish astronomer named Balfour Stewart, who was in a vigorous debate with other scientists about the nature of sunspots. Some scientists thought that the interior of the sun was cooler than the exterior, and sunspots were windows to the cooler interior, whereas Stewart and others thought they were from areas of thicker and cooler atmosphere, which absorb more sunlight. In March of 1866, Lockyer decided to use spectroscopy to solve this mystery. Now, he knew that sunspots weren't actually spots of no sunlight. Just like any other shadow, they're merely an area of less light than the area around it, although the brightness of the rest of the sun makes them appear black. Therefore, Lockyer used his papier-mâché telescope to focus the light from the sun on a screen and then placed a little hole in the screen so that the light from the sunspot would go through it, and then use the prism to determine the spectrum of the light from that spot. He then found that the absorption bands from the sunspot were visible in the spectrum of the spot. They, moreover, appeared thicker when they crossed into the spot spectrum. In other words, the sunlight from the sunspot had more absorption than the rest of the sun. And in this way, Lockyer validated that Stewart's theory was right with spectroscopy. Before the success with the sunspot, Lockyer and Stewart had a conversation about the strange red flames seen around the sun in the total eclipse, and came to the conclusion that it must be masses of glowing gas in the corona. Lockyer naturally wondered if he could use spectroscopy to solve this mystery too. And in fact, some of his last words in his 1866 paper on sunspots were, "May not the spectroscope afford us evidence of the existence of the red flames which total eclipses have revealed to us in the sun's atmosphere?" It was logical that these flames were always there, but you couldn't see it because they were blotted out by the bright sunshine from the center of the sun. Lockyer hoped that if he focused the spectroscope on the edges of the sun, he could still see it. However, Lockyer said that he diligently swept round the solar disk in search of evidence of the red flames, but without result, a failure he attributed to the excessive brilliancy of the sun. He realized he needed a way to block the sunlight from the center of the sun without dimming the light from these red flames. Now, there was an eclipse predicted for August of 1868. However, Lockyer did not have the patience to wait for over 2 years to view the eclipse, nor did he have the funds to travel to India where the eclipse was visible. Instead, Lockyer came up with a clever idea about how to remove the continuous spectrum from the center of the sun without an eclipse. He knew that a prism spread out the light from the sun into its different colors and wondered about using more than one prism. With more prisms, the continuous spectrum would be dispersed more and therefore would become weaker. But he had predicted that the light from those red flames were from burning gas, and therefore, once you split them up with one prism, they would come into their distinctive bands of light that were at set frequencies. Therefore, if you use more prisms after that, they wouldn't be dispersed anymore because they were at a specific frequency. He thought that if you used a lot of prisms in a row, you can dim the continuous light from the sun without dimming the distinctive light bands from the glowing gas in the red flames. Lockyer immediately tried to blot out the sun with multiple prisms, but his equipment wasn't good enough. So he applied for and won a government grant in early 1867 to get better equipment. Lockyer immediately turned to his friend Thomas Cook, who had given him a lens for his papier-mâché telescope in 1862. But unfortunately, Cook's health was failing, and by the end of 1867, Cook had to give up on the project, and Lockyer had to turn to another telescope manufacturer. That is why Lockyer only received his special spectroscope with 7 prisms on October 16th of 1868. 4 days later, on October 20th, Lockyer used his prisms, and as he described it a few weeks later, quote, I saw a bright line flash in the field, and my eye was so fatigued at the time that I first doubted its evidence, although unconsciously I exclaimed, "At last!" The line, however, remained an exquisitely colored line, absolutely coincident with the line C of the solar spectrum. That day he also found two more lines, one nearly coincident with F and one near D, where the one near D was off the regular D line. Put a pin in that one, it's important. Lockyer published his findings as a quick note the very next day to the Royal Society of London. Lockyer had proven that the red flames around the sun were made of a glowing gas. Balfour Stewart was also excited and immediately sent a letter to a friend in France exclaiming, "Lockyer is triumphant. He found red flames with a new spectroscope." This letter, along with a second longer letter from Lockyer himself, with more details sent 2 days later, were read to the Paris Academy of Sciences 5 days after the first letter on October 26, 1868. However, because of delays in equipment, Lockyer's observation was actually 2 months after that total eclipse. Now, one of the scientists who did have the money to go to India and observe the eclipse was a 44-year-old French astronomer named Jules Janssen. Now, Janssen, like Lockyer, was very interested in spectroscopy, and this was the first full eclipse that happened after the discovery of spectroscopy. However, when he put it on the sun, he found to his surprise that those red flames were made of glowing gases. He sent immediately a telegraph to a friend, declaring, "Eclipse observed. Protuberances spectrum very remarkable and unexpected. Protuberances are of a gaseous nature." Then Janssen came to the same conclusion that Lockyer had done 2 years earlier. Namely, he realized that if those red flames were from glowing gases, he could remove the light from the continuous spectrum by using multiple prisms, which is exactly what he did 2 days later, which was nearly 2 months before Lockyer's experiment. However, as Janssen didn't know about Lockyer, he was in no rush to publish, and a few weeks later, he sent a letter describing this to a friend, and then he went on a scientific trip to the Himalayas. That is why, on the same day that Stewart's and Lockyer's letters about Lockyer's success were read to the Paris Academy, Janssen's friend was inspired to stand up and read Janssen's letter as well. This, of course, caused quite a commotion, and it inspired another astronomer named Hervé Faye to stand up and ask permission to explain the singular coincidence of the discoveries which have just been presented at the Academy. Faye then described how it was clear that Lockyer had come up with the idea first at the end of his paper about sunspots in 1866, but Janssen discovered it first, but had just not had the time to publish it yet. Faye added that you could split the honor in two, with Lockyer being credited for coming up with the idea, and with Janssen being credited with the first one to discover it. But Faye countered, "Isn't it better to attribute the whole honor to both of these two men of science who have separately, from thousands of miles apart, the joy of discovering the most astonishing way forward in astronomy that the genius of observation ever designed?" From this point on, scientists in France attributed the success equally to both men, which was an advantage to Lockyer, who was barely known in France. When Janssen heard about it, he took it very well, writing a friend that if he'd known about Lockyer's project, quote, "I would have immediately communicated by telegraph the results I was obtaining in India. I do not regret that Mr. Norman Lockyer has managed to confirm his ideas separately. I think he deserves it." The friend published the letter, and Lockyer began writing Janssen, and soon they formed a close and lifelong friendship. In fact, Lockyer's 1874 book on solar physics was dedicated to Balfour Stewart and Jules Janssen, writing, quote, "Encouraged by one friend, Stewart, I undertook the work that has brought me the other, Janssen." Meanwhile, Lockyer spent every clear day he could studying those red protrusions with a special spectroscope. He found that although it got thicker in places with those red protuberances or flames, it actually enveloped the whole sun. as it went around the entire sun, but was different from the rest of the sun, he decided it was part of the sun's composition and therefore needed a new name. In November 1868, mere weeks after his first observation, he suggested the name chromosphere, which a friend recommended to him as it literally means colorful sphere, and the name is still used to this day. Lockyer then found a fourth clear line in the chromosphere. So he had, in order of discovery, a line at C, at F, near D, and at G. However, when he looked closer to the sun's surface, he found way more lines, writing, "Judge my surprise and delight when upon sweeping along the spectrum, I found hundreds of the Fraunhofer lines beautifully bright at the base of the prominence." This made sense to Lockyer and validated the idea that the chromosphere was made of many different elements, but most of them were too heavy to get far from the surface of the sun. Or as he put it, quote, "The reason that these do not reach up so far from the body of the sun is their vapors are very much heavier than the gas hydrogen, which is the lightest terrestrial substance known." Still, one part of Lockyer's results was puzzling. 3 of the 4 bright lines he found far from the sun, C, F, and G, corresponded exactly with hydrogen, which was logical. But one line, the one near the double D of sodium, did not. What was this mysterious line? At first, Lockyer thought, as the errant D line was found far from the surface of the sun, it must be from hydrogen. Maybe at high pressure or high temperature or something. He didn't know. He wasn't a chemist. July 8th, 1869, Lockyer said that his bright line near D, which he observed on October 20th, 1868, was a hydrogen line, to which the editor George Gabriel Stokes added a footnote that just said, "Hydrogen?" ? Lockyer, as I said, was not a chemist, but he was very close friends with a famous chemist named Edward Frankland, and they did everything they could to recreate this new D line with pressurized hydrogen. But by April 1870, he and Frankland admitted that the new line could not be created with hydrogen in the laboratory. And then Lockyer gave a talk noting, "A line in the yellow of the spectrum will also be noticed. This is one which has caused a great deal of discussion, for it is not coincident with any known terrestrial substance." Meanwhile, 2 years earlier, while he was waiting for his special spectroscope to show up, Lockyer had published a very popular book on astronomy for school children. His job as an editor for The Reader had gone away when The Reader magazine went bankrupt. So Lockyer convinced his publisher to let him start a new science magazine called Nature. With his famous friends, this magazine became hugely popular and a place where many different controversies were hashed out. Lockyer remained the editor and owner of Nature for the next 50 years until his death in 1920. And the magazine is still going strong. According to Wikipedia, Nature is one of the world's most read and most prestigious academic journals. Anyway, in 1871, Nature published the inaugural address of William Thomson, also known as Lord Kelvin. And this is the first place that I can find any mention of the word helium. In this address, Thomson told how the eclipse of 1868 proved that a sensible part of the light of the sun is from glowing hydrogen and helium, where the word helium was in quotes, with a footnote that Frankland and Lockyer find the yellow prominences to give a very decidedly bright line not far from D. It seems to indicate a new substance, for which they propose to call helium. For many years, scientists thought that helium was only to be found in the sun and stars. But then, in 1881, an Italian scientist named Luigi Palmieri published a paper stating that he had found helium on Earth while studying material from a volcano. However, the discovery was completely ignored by scientists in Germany, England, and France, and many people only mentioned it in retrospect. For Lockyer, he only learned about helium being found on Earth in 1895, 26 years after they named it, when a Scottish chemist named William Ramsay discovered helium while trying to create argon gas. Ramsay immediately gave a vial of the new substance to Lockyer, to examine as a sign of respect, although Ramsay was a far superior chemist and had already determined that this was helium with accuracy. 6 months later, some Swedish chemists, using a different method, managed to get enough helium to determine its atomic weight, which you can only do if you have it on Earth. And they found that yes, helium is very, very light. Second, only to hydrogen. And that is how Norman Lockyer became famous, named and discovered the chromosphere, named and discovered helium, and named and created the magazine Nature. So that was my video about Norman Lockyer. I hope you enjoyed it and have a great time at the observatory.